This is on, right? Okay. Somehow the number of students looks less, no? Number of students looks less, no?
It's less.
I think so.
Fluctuates.
Okay. 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 Are there questions from last time? Did you have a chance to look at the notes that I posted and the exercises that I have assigned? I think they are downloadable from the link. So Matteo, so the link, they must have gotten the link
Do you have the link? Raise your hand.
Oh, okay.
Who does not? Who does not have the link? Okay, ask your friend to give you, to pass the link.
Achha. Okay, so how many of you had a chance to look at the notes? Okay. So only very few. So therefore, the rest, of course, did not have chance to even look at the exercises. Okay. So is it a fair thing to ask, are there questions from last time? Because you didn't care to look at the notes. So, okay, so, but anyways, so we were talking about this thing called limit cycles, stable limit cycles. And we discussed this example of the Van der Pol oscillator. And we said that in the phase space spanned by the dynamical variables x1 and x2, where x1 is equal to x and x2 is equal to dx dot. Okay. So you have a closed, you have a closed trajectory, something of that sort, such that if you start from some initial condition, you will be eventually attracted towards the limit cycle. Okay. So what happens is that the dynamics will, the trajectory will asymptotically approach the limit cycle. So you start from outside, you will be attracted towards this orbit. If you start from inside, you will be attracted towards this orbit and so on. So we worked out the form of the limit cycle oscillator, at least for the case when mu is much larger than 1, which is the strongly nonlinear case, where this one shows what is known as relaxation oscillation, that there is fast discharge and slow build up and fast discharge and so on. So that was one limit that we discussed, and there was another limit, which is the weakly nonlinear regime, mu much smaller than 1, in which you can also work out the shape of the limit cycle. It looks almost like a circle, excepting that it's not closed. So the radius of the circle keeps increasing as a function of time. And in the notes, I had spelled out a way to get the form of this using what is known as the multi-time scaling analysis. I was hoping that you will go through the notes, because I think it is explained fairly well there, and there was an associated exercise. So one way to know if you have understood this multi-time scaling was to see if you are able to work out that example. And so please try that exercise, and if it is not clear, then we can go over it. But you have to take the first step. I'll take the second step, but not the first one. Okay, so that's fine. So what I'll do today is to generalize this notion of limit cycle to a general nonlinear dynamical system, not specific to any particular model like the Van der Pol oscillator, etc. Just to remind you once more that these limit cycles are very much a characteristic feature of nonlinear dynamical systems. In linear systems, we saw the example of the simple harmonic oscillator. You don't have a concept of a limit cycle. You have closed orbits. You do some perturbation, you go to another closed orbit. But there is nothing that says that you move away from a closed orbit and the dynamics pulls it back to the closed orbit. Such a feature is not there. So let's then come to the general notion of limit cycle and how to characterize it for any nonlinear dynamical system. So the plan of today's lecture is the following, that what I'll do is that I'll first talk about limit cycles in full generality. How do you define it for a general nonlinear dynamical system? How do you characterize it? How do you define its frequency and what's the amplitude of oscillation and so on? And then I'll discuss what happens when you have a limit cycle that has got a characteristic frequency and you subject it to a periodic driving. You know what happens when you have a simple harmonic oscillator and you subject it to a periodic driving and there is damping. Now I will see what happens if you have a limit cycle oscillator and you subject it to a periodic driving, and that would lead to what is known as the Adler equation, and it would give us an idea of how to do, how to analyze systems using time scale separation and integrating out fast degrees of freedom and retaining the slow degrees of freedom and so on. So, okay. So let's say a general nonlinear dynamical system, linear comprising, let's say, n degrees of freedom or n dynamical variables, let's say, which I call x alpha, where alpha goes from 1 to up to n. Well, n doesn't have to be large or anything. There is no thermodynamics. I mean, it could be just a single dynamical variable or whatever. So a general nonlinear dynamical system is described by an equation of this sort. A function which is, let me so these are the dynamical variables and they evolve in time given some according to some function f alpha, where a linear dynamical system will be ones in which all the f alphas are linear in all the x alphas. Okay, so there are n such f alphas, f1, f2, f3, f4. In general, f1 is a function of x1, x2, xn, f2 is a function of x1, x2, xn, and so on. And if all the f alphas are linear in all the x alphas, then you call it a linear dynamical system. For example, simple harmonic oscillator. So it's a two-dimensional system because there are two dynamical variables, x and p. You have dx dt is equal to whatever p by m, and p dot is equal to minus omega square x and so on. Okay. And when do you call it nonlinear? You call it nonlinear when this f alpha, like there is at least one f alpha which is nonlinear in at least one x alpha. That is, when these functions are not linear, like any one of them being nonlinear makes it nonlinear. Okay, 1 minute. What happened? 1 minute. Let me just. Okay, so now this is a very particular class of nonlinear dynamical systems. So these are the ones that I will consider. You see that there is no explicit time dependence on the right hand side. Okay. These functions are time independent. So they are more specifically known as autonomous dynamical systems. Autonomous in the sense that there is no explicit time dependence in these functions. So what is the feature that like emerges if you have a nonlinear dynamical system that is autonomous? So why somehow this is keep rotating? Okay. Yeah. So what will happen is that, if x alpha t is a solution, I'm just sticking to my notation in the notes, then if this is a solution, then if it is an autonomous dynamical system, then this one also will be a solution, and this will have strong implication in what I say later. This is also a solution for arbitrary T naught. So that is to say, your origin of time is immaterial, which is very much physical in the following sense, that this function doesn't depend on time. So it doesn't matter, when you start integrating your equation from in terms of time. Okay, the origin of time is completely immaterial. So therefore, if x alpha t is a solution, you translate t by some arbitrary amount, and that is also a solution. Huh. See, this has nothing to do with being linear or non-linear. It just says that if this function doesn't depend on time, then the origin of time is immaterial. Okay, it is true for linear as well as for non-linear. Okay? And that's what you do, right? When you integrate your equations of motion for a harmonic oscillator, you integrate it from 0 to t, but you may as well integrate it from 5 to 5 plus t, and you would get the same answer. Everything depends on the time difference. The origin of time doesn't matter. So this autonomous has nothing to do with the system being linear or non-linear. It has to do with the fact that the function doesn't depend explicitly on time. It depends implicitly on time because the x alphas themselves change as a function of time. So they do have an implicit dependence on time, but no explicit dependence on time. So for such a system, you will have an n-dimensional phase space. Can somebody tell me what will be the axis of the phase space, like this n-dimensional phase space? What are the different axes of this phase space? X alphas, right? So x1, x2, x3, xn, right? So you have this n-dimensional phase space. Okay, so call it gamma space or whatever. And so then these limit cycles, what are these limit cycles? To have limit cycles, you need the system to be nonlinear. So that is to say that this, the system, it cannot be a linear system. So the f alphas, not all f alphas can be linear in all the x alphas. There should be at least one f alpha which is not linear in at least one x alpha, and so on. So these limit cycles, these are what? These are periodic, closed orbits, periodic orbits or closed orbits, whatever you say, in this phase space. So which is an one-dimensional object, okay? Because in an n-dimensional phase space, it's just a line that keeps coming back. Like if you start somewhere here, exactly on the limit cycle, you go around and you come back to your initial point. Now the question is, and it will have, so it's what is limit cycle? So it will be one-dimensional periodic orbit with some time period t. Now what I want to do is I want to characterize the dynamics on the limit cycle. How do I do it? Like, what is the variable that I should look at to see that, it is changing and then coming back to its initial value and so on. Okay, of course, since it is a one-dimensional object in this high-dimensional space, n-dimensional space, so what I can do is that my origin of time is irrelevant. So what I can do is that I can mark some arbitrary point on this closed orbit, okay, and I call it time t equal to 0, and what I can do is that I can keep measuring the length of this orbit starting from t equal to 0 as the system goes round and round. Okay. So that leads me to this concept of this arc length s of t, since it's an orbit in an n-dimensional space. So the total segment, the length of the total length of the segment traversed in time t, that would be simply given by this guy. Let me just write it down, and you will at once recognize that this is what it should be. It's just the Euclidean. Right. So this is, you take a small segment, and the length will be what? Dx, dx1 square plus dx2 square plus dx3 square, whole of it, square root of it. So I want to integrate in time because I want to get what is the total length of the segment that is traversed in time t. Now the problem with this definition is that it may so happen, see, there is nothing that says that dst dt, if I take the time derivative of this guy as a function of time, this is going to be uniform around the limit cycle. That is in the, so let me just draw this limit cycle a little bit bigger. So what it says is that there is nothing that says that in the same time interval delta t, exactly an equal length of the segment will be traversed. This is also in delta t time interval, this is also in delta t time interval, but there is nothing that says that the motion has to be uniform such that in delta t time interval the length of segment that is traversed is always the same. That is to say, at 10 o'clock if I ask what is the length of the segment that is traversed in the next 5 minutes, maybe I get 5 centimeter. And then if I ask at 2 o'clock what is the length of the segment that is traversed in the next 5 minutes. So delta t is always the same, 5. But then in one case I am asking the question at 10 o'clock, in the other case I am asking the question at 2 o'clock. And there is nothing that says that the length will be the same. That is to say that ds dt doesn't have to be uniform around the limit cycle. Okay? But I want a variable that is uniform around the limit cycle because that makes my life easy. Why, how, I will see. But let's see if there is a way to make a transformation from this variable to some other variable that has that property. Okay? Can you think of a motion in which in the same time interval delta t an equal amount of segment is, equal length of segment is traversed? What sort of motion is that? Huh? Circular motion, right? Circle has this property that in 10 minutes the angle changes by the same amount no matter when you are asking the question, right? But there is no reason why a general limit cycle has to be circle. It could have some, it's a closed orbit, that is the only defining thing. So it doesn't have to be circle, and if it is not a circle, there is nothing that says that this length and this length has to be the same. They have to be the same. There is nothing. But let's see if there is a way to make a transformation to some other variable that has that property. And indeed there is a transformation. So what you do is that given s of t, you transform to a new variable theta, which is a function of s. That is, what you do is that you fix your time, you find s by doing this integration, and then you define this variable theta, which is a function of s, and it is defined in the following way: pi by t of 0 to s of ts prime So this is the definition. Okay. So what you do is that you find s, and then you define a new variable theta, which is that you integrate from 0 to s of this guy. Okay. So what it will do is that you see the ds dt, the velocity part, how much does the arc length or the segment length change in a small time dt, that is appearing in the denominator. So what will happen is that it will give more weightage when small distances are traversed and smaller weightage when larger distances are traversed. What is the utility? If you take this definition and if you ask what is the time derivative of theta with respect to time t, so you can do this quite like easily, and what you will find is that this will just be equal to twice pi by 2. Can somebody do it easily? D theta dt, how will you do it? What is the way to get, given this function, if I want to know how does theta change as a function of time, what is the thing that I should do? And I claim that the answer is twice pi by t, the prefactor that's appearing here. What I should do? This is the, how does the arc length change as a function of time measured at location s prime, when the distance that has been traversed is s prime, and then you integrate. Okay? So, this is the local velocity. This is the local velocity when the distance that has been traversed is s prime, and now I just add them up, taking the inverse of that. And what I claim is that if I now take the derivative of theta with respect to time, I am going to get a number that's constant, and that's the thing that I was after, a uniform motion. So I am asking, how do I get this, how do I compute this derivative, d theta dt? Absolutely. So what you do is that you say this is nothing but d theta over ds and ds over dt. And well, if you do d theta over ds, so basically you like evaluate it at s, right? You evaluate the integrand at s. So what you will get is you will get twice pi by t, 1 divided by, see this d theta ds will give me twice pi by t of the integrand evaluated at s, which is ds dt. But then there is another ds dt hanging here, so these cancels. So what you get is twice pi by t. Fine? Nothing mysterious, right? So what I am able to do is that not necessarily my limit cycle is a circular orbit. It could have any arbitrary shape. The only thing is that it has to be a closed orbit. And one way to characterize it, its motion, is to measure the length of the segment that is traversed in time t. This part is not so visible. Should I somehow write? It's okay. Some of you are standing. Okay. Anyways. So therefore, what I have been able to do is to come up with a variable theta that measures, somehow it is intimately related to the distance that the phase space point traverses along the limit cycle, starting from some arbitrary starting point, and the rate of change of theta is uniform. So therefore, what I can claim is that given any nonlinear dynamical system, I can always do that transformation, because in there I did not use any particular form of the functions or any particular form of by the way, one thing that I have been doing, I mean yesterday I did it and today also I have done it, which is that I am always writing down equations in terms of first order differential equations in time. Is it very general? It seems like a very specific thing to do, no? That I'm always talking about dynamical systems in which the equations of motion are always first order in time. Is it very general? Can we not have second order or third order or 76th order differential equations in time? Absolutely. So it doesn't matter. So if I have a second order differential equation in one variable, I can always write it as two first order differential equations in two variables which are coupled. So if I have a fifth order differential equation in time, I can always re-express them in terms of first order differential equations. Okay? So therefore this is very general. I am not being very specific, very particular or anything. So therefore this is very general, and therefore the definition of the limit cycle is very general, And the way I characterize it in terms of an angle like variable that changes, that changes uniformly in time, that is also very general. It doesn't have to deal with any particular form of the dynamical system. Okay, so let's just did I keep it? Do you see the dust? Okay, yeah. So my limit cycle will be characterized by an equation of motion of this sort. Omega, where omega is equal to twice pi by t. T is the time period of the limit cycle. How much does it take to come back to its initial location after a certain time? One thing I forgot to mention, you can check that if S of t is the value that S takes after you have traversed a complete time period, so let me call it as 0, then theta is 0 is equal to 2 pi. That also you can check quite easily. That is to say that when the trajectory completes one motion, okay, one period, okay, theta also increases by an amount 2 pi. So everything is perfect, okay. The original motion did not have any uniform thing, like the S was not changing uniformly, but I can always transform to an angle like variable that changes exactly by an amount 2 pi when the trajectory completes one period. And the equation of motion is of this sort. So theta is an angular variable that lies between 0 and 2 pi. But you see, the problem with this description is we are not so much interested in the motion on the limit cycle, because limit cycle, you are never on the limit cycle. Typically you are away from the limit cycle, and the claim is that if you are away from the limit cycle and if it's a stable limit cycle, the dynamics is eventually going to pull you towards the limit cycle. So asymptotically you will approach the limit cycle. You will of course never coincide with the limit cycle, but as time gets larger and larger, as you wait longer and longer, the deviation of your trajectory from the limit cycle will get smaller and smaller. But the question is, see, I am interested in the dynamics of my trajectory, not a trajectory that starts exactly on the limit cycle. So what is the guarantee that this equation that describes the motion on the limit cycle is also applicable to motion away from the limit cycle? Maybe there is nothing, right? A priori, I mean, this is what you would think is, okay, this is true for a motion on the limit cycle. It doesn't have to be true for motion slightly away or a little bit away from the limit cycle. But it does hold also for trajectories which are slightly away from the limit cycle through a construction of an entity called isochrone or isochrone. So which plays an important role, and that's what makes this synchronization studies possible. So what you have is, you have your limit cycle, right? Okay, let's say the limit cycle is traversed in the clockwise direction like this. So what I want to do is, what I know is that if I start away, if I start exactly on the limit cycle, I remain on the limit cycle. Theta changes by 2 pi every time I come back to my initial location after a time equal to the time period t, and everything is fine. But what happens if I start away from the limit cycle, and then the claim is that I should approach this asymptotically. So what I want to know is, does this kind of description also apply to trajectories which are slightly away from the limit cycle? So let's see how it works. So let's take a trajectory. Okay, so this is one trajectory. So it goes around and then it comes closer, and second time also it comes even closer, and so on. Okay. Okay. So what I do is that I look at the the state of my, so this is my starting phase space point, okay? This is the point from which I initiate my dynamics. So what I do is that I look at the state of the system, the phase space coordinates stroboscopically. That is, I look at the point after a time equal to t. So look at the phase space point stroboscopically, meaning not at every time instant, after every time interval equal to the time period of the limit cycle. So let's say I start from here and it goes round, so next time the point is here, and it goes round, so next time the point is here, and so on. Do you see the construction? Is it okay, the construction? So what I do is that I locate a point and I see where does the point go after time has passed by an amount equal to t. So this point now comes here and comes here and so on. Okay. So what I get is I get a sequence of points, the limit of which is a point that lies exactly on the limit cycle, right? Because this sequence of points, if I keep observing the phase space point after every time interval t, I'll get a point here, 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 and gradually I'll I'll get to a unique point on a limit cycle. So the limit of this sequence of points is a point that is unique on the limit cycle, and which has got a unique value of theta, and the dynamics of which is governed by this equation. Okay. So this gives us this leads to the construction of what are known as isochrones or isochrones. So what are isochrones? So these are manifolds, or this is in the n-dimensional space. These are like hypersurfaces or manifolds or whatever you want to call them, such that you construct them in the following way, that each point on the isochrone is obtained by observing the phase space point after a time has passed that is equal to t, and each isochrone cuts the limit cycle at a unique point. Okay, so for every theta there is a unique isochrone I theta. So there is one isochrone here, one there, one there, one there, and so on. Is the construction okay? So therefore what I can do is that if I am interested in the long time dynamics, and I am always interested in the long time dynamics, not so much interested in the transient dynamics, that is, I initiate my dynamics and at once I ask where does the system go, what is the state of the system. That's not what I am interested in. I am interested in letting the system run for a while and see where does the system go. And I am pretty sure in case there is a stable limit cycle that exists in the phase space, I am pretty confident that the trajectory will eventually approach the limit cycle. And I know that on the limit cycle there is a this is the equation of motion for the angle, and for every angular position theta there is a unique isochrone that I can construct. So therefore I claim that this equation of motion, it applies not only to motion on the limit cycle but also to motion away from the limit cycle, but not too away. Like if you are 10 kilometers away, no, not really. But then if you are slightly away, and that's what you are interested in, because in the long time state of the system, you will be close by, you will not be 10 kilometers away. Okay. So therefore this equation of motion applies to a very good approximation also to trajectories which are slightly away, that is in the close neighborhood of the limit cycle. So you can think of, if this is a limit cycle, you can think of a tube around it. let's say some tube around it, and inside this tube, if you take any trajectory, and if you ask, how do I characterize the trajectory, you better characterize it in terms of the corresponding limit cycle. Okay? This may sound very trivial, but actually on the face of it, it is not so trivial if you think about it a little bit. That you are describing something in terms of some other thing. You are describing apples in terms of oranges. And you are claiming that, well, apples will asymptotically approach oranges. It turns out that in this case, indeed, apples are asymptotically approaching oranges. So therefore, you are in good shape. But on the face of it, it doesn't have to be so. Is this construction clear? Sorry, I theta? I theta. No, I theta gives you the equation of motion, the equation of this manifold. Okay, how do you define this manifold? How do you construct this manifold? To construct this manifold, see, why do I call it I theta? Because for every theta, there is going to be a surface such that every point on the surface asymptotically approaches a unique point on the limit cycle with the angular position theta. Okay?
So, I do understand the argument that you said for generalizing this equation of motion to another curve that is asymptotically close to the limit cycle.
Achha. The argument is the following. You see, every point, what you can do is that I know the equation of motion of this point. Okay, this equation of motion is this one. Okay, but then this point is uniquely related to this one, and this one is uniquely related to this one, and this one is uniquely related to this one. So therefore, if I know where does this point on the limit cycle go in the next 5 minutes or so, I know uniquely, for sure where does this point go, because there is a one-to-one mapping between them, the way I have constructed. So therefore, it suffices to know where does this theta, this angular position on the limit cycle, where does it go in course of dynamical evolution, because if I know this and I know this isochrone, I know at once where does this point go in the next dimension. Yeah, because for every theta you can construct a isochrone. So they are densely filled up. I am leaving gaps because I want you to see them as separate, but actually they are, for every theta there is an I theta function. Okay? Huh.
Same construction is available inside the circle?
Yes, inside also, if it is so that's why I drew this tube. See, if it is a stable limit cycle, so inside, so let me just draw what will be the, okay, it's already there. So inside, of course, I mean, that's why I wanted you to work out the exercises. You can show that for the van der Pol oscillator, there is a fixed point at 0, 0, which is unstable in some mu regime. So what will happen is that if you, so this is your limit cycle, if you are here, so you will gradually move outward towards this. And again, I can draw this isochrone. Okay, from outside you go inward, from inside you go outward. So therefore, I can do the same construction. Yes, it is stable. We are always talking about stable limit cycles. Unstable limit cycles are not much of interest because anyways you don't get there. They exist. If you are there, you stay there. But then if you are away, you are pushed out. So therefore, they are not so much of interest to us. So I hope you are, appreciating the progression that I am making. What I want to do is, okay, let's come back to the big picture that I want to build eventually. See, what I want to do is I want to get to this phenomenon of synchronization. And as was shown yesterday in the videos, in synchronization, what you have is you have many, many metronomes or many, many cardiac cells. Each one is exhibiting some oscillatory motion, which is to say in terms of this limit cycles that you have many, many limit cycles. Each one has got a different value of frequency. Okay? So the eventual picture, so let me just draw this eventual picture because that's probably will. So you have one limit cycle which has got frequency omega 1, you have another one which has got frequency omega 2, you have another one which has got frequency omega 3, another one omega 4. Okay, there are many such limit cycles. They need not all go in the same direction. You know, if it is negative, it goes in the other direction. Okay, and you have many such units, and there is some interaction between them. And the question is, under what conditions will this collection of limit cycles start to show synchrony, in the sense that there will be a common frequency of oscillation of all of them? Or more precisely, if I want to know how does the phase of the limit cycle, each individual limit cycle change as a function of time, I should be able to show that the phases change maintaining a constant phase difference. Then I will say that the system is synchronized. And why it is surprising that such a thing, you know, you may think that such a thing should not happen. Why it should not happen? Because if the frequencies are too different, and if there is only very weak interaction, think of the metronome example. The metronomes are placed on a wooden block, and so the only way one metronome gets to know about another metronome is through the motion of the atoms and molecules, that are the atoms and molecules which are set into motion through the contact of the first metronome with the wooden block. So it's a very, very weak interaction. Okay. So the picture is clear. What is it that we want to get to? There are many such limit cycles. Each one has got a different frequency. So what is the thing now that I have told you? What is the equation of motion of this guy? This equation of motion is d theta dt equal to omega 1. This one is d theta dt equal to omega 2, and so on. So what is the next thing that I should worry about? Interaction. What should be the form of the interaction? Right? They have to somehow interact with one another. What should be the form of the interaction? So the first thing that we note is that these are not Hamiltonian systems. Okay? These are nonlinear dynamical systems, so you cannot write down a Hamiltonian function and then take the derivative h, which is a function of all the thetas, and then you say minus del v del theta, where h has a potential energy contribution, and therefore the force is due to some inter-oscillator interaction, and I take that interaction potential, I take the derivative with respect to theta, negative of it, that gives me the force or the torque. That's the first thing to do, right? You have many elements, but what is the Hamiltonian of the system? There is no, these are not Hamiltonian systems by themselves. These are dissipative systems. This is dissipative, this is dissipative, this is dissipative, this is dissipative. Remember, you needed dissipation, right? Because in the van der Pol oscillator, you need energy pumping and dissipation. That is to say that you need a dissipation term that switches sign. Sometimes it becomes positive, sometimes it becomes negative. And why did you need dissipation? Because what dissipation allows you is to settle the system into a state which is independent of the initial condition. So the state, the long time state, is the state in which there is a balance between energy pumping and dissipation. Positive damping or positive dissipation and negative dissipation. Huh?
Sorry, can you define this synchronization in this context again?
Okay, fine.
Are we talking about points which are on the limit cycles, one of them, or in the neighborhood?
Okay. So what I want is that I will never, consider, if you are exactly on the limit cycle, of course, I mean, this is the equation of motion, but what typically what you would do is that in the long time dynamics of the system, you would be considering trajectories which are very close to the limit cycle. Okay? And the thetas are changing as a function of time. I construct, the way I constructed the isochrone. Okay, so this has got a theta. The equation of motion of that theta is, I can study that dynamics in terms of this equation through the construction of isochrone. Okay, so there is one set of isochrone that I can construct, and therefore if I know how does the motion take place on the limit cycle, I know through the construction of the isochrone how does the dynamics take place slightly away from the limit cycle. Okay, so this is one limit cycle. It is going around with its own dynamics. This one is going around with its own dynamics, and so on. So this one theta, so what is the solution of this guy? the solution will be, let me call it, this is the first oscillator, so call it theta 1, theta 2, theta 3, etc. 1 minute. So theta 1t, if I just integrate this equation, this will be this. Fine? Okay, and similarly for this one. By synchronization, let's talk about just these two oscillators. What does synchronization mean? It would mean that the phases, so if I look at the phase difference, let's look at the phase difference. Theta 1t minus theta 2t. That would be equal to omega 1 minus omega 2t plus theta 2 0 minus theta 1 0. Now omega 1 is not equal to omega 2, so this is a constant number, okay, this does not change with time. So therefore, there is no reason why the phase difference, the difference in the phases of the two oscillators will remain constant in time. It will not remain constant, it will change, right, because omega 1 is different from omega 2, fine. So what would happen is that if I denote these phases as points on a circle, okay, so what I do is that I draw a circle where a phase is a point. Why I do it? Because phases change by 2 pi. So therefore, this circle will just go around with a frequency. For the first one it will be omega 1, for the second one it would be omega 2. So what you will see is that you start from, let's say this one is my theta 1 0 and this one will be theta 2 0 and this one will go around with frequency omega 1 and this one will go around with frequency omega 2. Okay, so they will cross each other and so on. So there is no way in which the 2 points will move in such a way that there is a constant phase difference among them. It's not possible. It's not possible. Why? Because omega 1 is different from omega 2. Right? But if I can somehow bring in some interaction such that the interaction is able to counter this effect, such that when I look at the motion here, I see 2 points, they are maintaining a constant phase difference in time, then I will say that the system is synchronized. So therefore, if I look at the the frequency of each one of them, the observed frequency, not the natural limit cycle frequency. If I ask how much does this guy change, what is the frequency of this guy, what is the frequency of this guy, I'll get the same value. Why? Because they are changing, the phase difference between them remains constant in time. Okay, there are several things. Okay, these are angles. Does that make no, the phase space and this phase, these are different things. Is that the confusing part?
I think the confusing part is that how are we going to realize the interactions in a phase space? Like how are we going to see that, because that doesn't seem to be clear.
I haven't talked about interaction yet. Okay, so this guy has got its own phase space. So this limit cycle, it exists in its own phase space. This is a 56 dimensional system for which I have a 1-dimensional orbit. This is its own phase space. This is a 752 dimensional nonlinear dynamical system. It has got its own phase space where there is this thing, and this one has got, sorry? Not 1 point, 1 orbit. No, it's not 1 point. No, if it were 1 point, it would have been a fixed point. You have an orbit, stable orbit. Yeah, 1 point. You start from 1 point, and at any given instant, of course, it's 1 point. Yeah, at any given instant, you are either here or here or here or here. Okay, so you just see this one going around, this one going around, this one going around, this one going around. And now I have to talk about interaction. What is the form of interaction? So the point, now before that, like, is this picture clear? Somehow this, this sort of synchronization and phase space, it is, I don't know, somehow, nonlinear dynamics, it is usually not taught in a university curriculum. So there are concepts that are simple, but then still, I mean, so if something is unclear, then tell me before I move on to interaction. We can, let's go one by one. How many of you have not understood limit cycles? Now, okay, limit cycle, like I am not saying that, okay, you have understood every part of limit cycle, everything, there is nothing left. Nobody has understood everything of everything. So, of course, but at least you have a working knowledge of what a limit cycle is. How many of you have not understood what a limit cycle is? You all have understood. Okay? It's a very simple object that you take a nonlinear dynamical system. It could be a system comprising 5 degrees of freedom, 56 degrees of freedom, whatever. Okay? It has to be nonlinear. Nonlinear is important. And if it is a nonlinear dynamical system, then what's a limit cycle? That you go to its phase space and you see that if you initiate your dynamics with some initial condition, then what you see is that asymptotically, that is as time progresses, this one point seems to approach a closed orbit in this phase space. As simple as that, that you have a phase space, there is a closed orbit and you start your dynamics from some point. If it so happens that that point goes round and as time progresses approaches a closed orbit, you call that closed orbit a stable limit cycle. This part is clear? Now, of course, you have a closed orbit, so therefore you can uniquely define a time period of that orbit by simply asking how long does it take to come back to the starting point. For example, there is an orbit that takes 10 minutes to come back to its initial point, so therefore the time period is 10. For some other orbits it could be 500, whatever. Okay? So then what I said, what I discussed today is that you can describe the dynamics on the limit cycle in terms of an angle-like variable, theta, such that the equation of motion is d theta dt equal to omega. That part was clear? You are exactly on the limit cycle. So if you are exactly on the limit cycle, you can define a phase-like variable theta which changes uniformly in time with period equal to the time period of the limit cycle. This was okay? How many of you feel this is not okay? Again, the negative one, because again I want the positive answers. It's okay. So then I said that, okay, you are on the limit cycle, the equation of motion is d theta dt equal to omega. What happens if you are slightly away from the limit cycle? Can I still use the same equation of motion if you are slightly away from the limit cycle? And I said that yes, you can still use the same equation of motion provided you are not too far from the limit cycle. If you are close enough, then you know you can use the same equation of motion, no problem. So now what I have is, I have several such limit cycles. Each one has got its own characteristic frequency. Think of this as metronome 1. Think of this as metronome 2 and metronome 3 and metronome 4. Okay? So these metronomes, I hope you recall the video that I flashed yesterday. What you do is that you give each of the metronomes a kick. But then you are not very consistent and sometimes you are too angry, so you kick it hard. And sometimes you are mild and so you don't kick it so hard. But anyways you kick them. Okay, there are five of them and you kick each one of them differently. So that is your initial condition. And what you found is that eventually all of them seem to be moving in synchrony, and by synchrony what I mean is that if I look at the phase difference, the difference in the phases of the different metronomes or the different oscillators, synchrony would simply mean that the phase difference will be a constant in time. It doesn't change as a function. And on the face of it, if there is no interaction, such a thing is impossible. As I have shown here, see, for this one the equation of motion is this, for this one it is that, and so on. So if I just solve this, and this is one of the reasons for wanting to go to a angle-like variable that changes uniformly in time. Why? Because integration becomes damn easy. Right? Because this is a constant. This is just 2 pi by t1, the time period of this oscillator. I don't have to, and look at the, the definition that I had for s of t, that was more complicated. To do this integration, I have to, work hard and so on. So what I have to this one was the definition, no? Action, which one?
In gravitation, people consider action as like they try to find the trajectory in the space.
So you see,
Find the minimum action.
okay. So first of all, when you would like to write down an action when there is there's an underlying Hamiltonian function. You need that, right? A Lagrangian. So these are not Hamiltonian systems. You have dissipation, right? So action principle doesn't apply to these systems.
So like you cannot find a way around it.
No, you cannot find a way around it because these are dissipative systems. Energy is not a constant. You cannot even define energy. I mean, how do you define energy for van der Pol oscillator? And even if you are able to define, it doesn't remain constant as a function of time. These are not Hamilton equations. That is to say, okay, these are dynamical systems. And by the way, you cannot also apply statistical mechanics. Like somebody was asking, the gentleman was asking if there is a function that you can minimize or maximize, like there is some entropy, free energy, etc. So those things are also not available here. These are not Hamiltonian systems. The number of degrees of freedom doesn't have to be very large. There is no concept of thermodynamic limit and so on. So I hope the synchronization part is also okay. This integration is fine. This integration is fine, and therefore the difference is also fine, I guess. Right? So what it says is that if I look at the difference in the phases of two oscillators, there is a time dependent component here. So there is no reason why the phase difference, there is no way in which the phase difference can be constant in time unless omega 1 is equal to omega 2. But if omega 1 is equal to omega 2, you are asking about synchronization among twin brothers, okay? Like the two are identical, then they are obviously synchronized. Then there is no, why are you asking the question? Okay? So the question is, you have dissimilar elements, fireflies. One firefly doesn't care about the other firefly, so they are dissimilar. Omega 1 is quite different from omega 2, and yet can I come up with a mechanism such that theta 1t minus theta 2t, this quantity becomes time independent. Obviously in this setup I cannot do it, as I just, so what I have to do is I have to somehow make them interact with one another. Now the question is, what should be the form of the interaction? How can I derive a form of this interaction from first principles? There is no Hamiltonian function, so I cannot say that there is Coulomb interaction between them, so you take the del R or whatever and then you put it. Or there is some, I don't know, some long range interaction, something that you can cook up. No, those things are not there. Okay? Yeah. Sorry, you had a question. Sorry, I somehow glossed over. What I do is that, okay, it's quite easy to do numerically. What I do is that I start my dynamics. So you are asking how do I construct an isochron? So it's quite simple. So I have this closed orbit. Okay, I have my, let's say I take the van der Pol oscillator with mu larger than 1. Why don't you do it as an exercise? Because then, once you do it, you know that it can be done. Otherwise, whatever I say, you will say, okay, he says it can be done, but I could not do it. So you do it. So what you do is that you start from some initial point, okay? What you do is that you decide to look at where does this point go after a time equal to the time period, okay? So this point, it starts here and it goes round. After one period, it cannot join this point, because if it had joined, then this trajectory would have been closed. But it is not closed. This is the closed orbit. So therefore, after time t, it comes here. Okay? So you note down that, you note down, let's say you start from x equal to 5, y equal to 7, whatever. After you come back, you maybe x becomes 3 and y becomes 2.5, whatever, okay. So then you mark, you note down the point and then you let the dynamics evolve again, and then you note down the point again and then you let it go and so on. So you will see that the limit, the sequence of these points, there is a limiting point that the sequence approaches, which is a point on the limit cycle. It has to be there, because otherwise there is no point in saying that the limit cycle is stable. If the sequence doesn't approach a point on the limit cycle, there is no notion of stability. I mean, I cannot say that it's a stable one. So what I say is that, so I have this sequence of points, so what I can do is that I can construct this manifold, this sequence, let's say a set of numbers, such that the limiting value is a value on the limit cycle, and I can do it for every point on this limit cycle. So this is the construction of isochron. And I know how does this point on the limit cycle change as a function of time. So therefore, through the construction of isochrons, I know how does this point also change. Of course, I cannot be very far away. I mean, then of course it doesn't. So the best thing is to do it. That's the best thing. I mean, to actually sit down, it doesn't require, I mean, you to know, you can do it on Mathematica or so on. So what you do is that you start from some initial condition and you look at the location of the phase space point after a time equal to t has passed. You note down the point and you will see that these real numbers, they tend to approach a point that lies exactly on the limit cycle. In fact, I have given you for mu much smaller than 1 an equation for the limit cycle. How does the limit cycle look like? It's almost a circle. So you know what a point on the limit cycle looks like. Okay. So then I have to come to this question of how do I make them interact with one another. So then let's do this part. So there is one small section on what happens. You may wonder, before going to many limit cycles which are interacting with one another, before going to many, what is the first thing that you do? 2, right? So what happens if you have 2 limit cycles? They have their own frequencies and I somehow couple them, and I want to know what should be the form of the coupling. Can it be any arbitrary thing? So that I have to figure out. But there is like another step that you may take, I mean a step back, which is to say that I have a limit cycle which has got its own frequency, and then I subject it to an external periodic force. Okay. So this thing is worked out in the notes, so I will not get into that. So this leads to something known as the Adler equation and Arnold tongue and so on. So in the quantum case, of course, we will need the concept of Arnold tongue. So maybe I'll talk about it when I get to quantum. Let's first get to these 2 limit cycle oscillators and try to get a form of the interaction potential. Not interaction potential, the form of the interaction. So this one has got the frequency omega 1 and this one has got the frequency omega 2. Maybe this one is being traversed in the clockwise direction, this one is traversed in the anti-clockwise direction. Okay. So let's try to write down the equation of motion for these guys. So d theta 1 dt equal to omega 1 plus something, and I'll write down what that plus is. Equal to omega 2 plus something. So what is that plus? That plus will be the interaction term. Okay. So that interaction term, let me write it in terms of some function g1, which of course will be a function of both theta 1 and theta 2. And some function g2 which will also be a function of both theta 1 and theta 2. But then I need to put in a small parameter somewhere because I want the interaction to be weak. So what I do is that I put a small parameter epsilon here with the understanding that epsilon is much smaller than 1. So this epsilon much smaller than 1 enforces the condition that the interaction between the 2 oscillators is weak. If it is strong, then you better not talk about 2 oscillators but 1. So therefore, I need to make that this thing. Okay. Now this function gk, where k, I will use this index k to mean either the first or the second oscillator. Okay. So this gk, you see these thetas, these are periodic variables, right? Each time time changes by an amount equal to capital T. For this one it would be T1, for this one it would be T2, but these are periodic. These gk's will be periodic, 2 pi periodic in theta. That is to say that and also individually also this will be true. Right, because theta, each time the motion completes one one complete traversal, theta changes by 2 pi, but you come back to your initial point. So what I do is that I introduce new variables. Can somebody from classical mechanics course, you must have seen, if you have 2 objects and they are interacting or doing something, then you tend to define 2 quantities. Can somebody tell me, you go to a frame or center of mass coordinates or something, you must have heard about it, right? When there are 2 particles which are interacting and so on. Yeah, you do. Yeah, but you go to the, so something similar we will do here. So let's see what do I do. Okay, so let me define 2 quantities, this theta, which is defined to be theta 1 plus theta 2 by 2. So why I do this will be clear in a minute, maybe not in a minute, maybe in 5 minutes. So that's okay. Okay. What is my ultimate aim? Okay, my ultimate aim is the following. You see, can somebody tell me what will be the dimension of epsilon in terms of time? See, epsilon will be 1 over time, right? So what I want to do is I want to somehow use the fact that because epsilon is small, that there will be some time scale separation. Where is the time scale separation? Where is it arising from? If I think of it physically, what is happening is that there are these 2 limit cycles and the motion is taking place, but because there is some weak interaction, so the limit cycles get slightly distorted. Right, because this is a weak, so I want to see this, I want to utilize or invoke this time scale separation, and as I will show you, this one is going to be a fast dynamical variable and this one will be a slow dynamical variable, and then we can do a lot of reasonable assumptions to, so in terms of these new variables, let me rewrite these equations of motion. So what I can do is that I can take the time derivative of this guy and this guy with respect to time and use these equations to write the equation for d theta dt, okay, this capital theta dt, that would be just half of omega 1 plus omega 2 plus epsilon by 2 of, before that let me write down the equation of motion. Is this clear? What I did was that here these functions, they depend on theta 1 and theta 2, but I replace for theta 1 and theta 2 these new quantities, theta and phi, and if I do so, my equation of motion looks like this. There are 2 such equations. Okay. And now using that, let me write down an evolution equation for this capital theta and capital phi. So the first one will be if at some point something is unclear, then tell. But there is no way in which I can skip this part, because this part is really quite relevant to understand, how do you get the form of the interaction from scratch, almost from scratch, because there is no underlying Hamiltonian and so on. Is this equations clear? How do I get them? It's clear, right? What I do is that I just take the time derivative of the left hand side and the right hand side, and for d theta 1 dt and d theta 2 dt, I just substitute these equations there. Fine? Okay. But now I use the fact that since epsilon is much smaller than 1, so therefore to leading order in epsilon, can somebody tell me what is the solution for this guy? Leading order epsilon, what would be the solution for these two guys? What would be the solution for what is this function? Let's see if you can get exponential out of these equations. Who said exponential? Okay. Do you get exponential really? See, epsilon is to leading order in epsilon. So which is the leading term here in terms of epsilon? Which is the term that is going to dominate the dynamics? In the first equation and in the second equation? The first term, yes, because epsilon is much small. So the leading term will be, the leading contribution will be given by the first term on the right hand side, both here as well as there. So to leading order in epsilon, this will have a very simple solution, omega 1 plus omega 2 t by 2. To leading order, there will be correction. And this one will be omega 1 minus omega 2 t by 2. This is to leading order, not that I am saying that, and there will be some initial condition, but that I can forget. I can say that let me start with an initial condition in which theta t equal to 0 is 0 and this is 0. Because anyways I will be interested in the long time limit, where it doesn't matter really what I do. Okay, so I need these two equations. So therefore, let us look at this equation now. Now gk, the original function was the cal g, right? Cal g was written in terms of theta 1 and theta 2, which I rewrote in terms of this normal g, in terms of this capital theta and capital phi. These are periodic functions. They are 2 pi periodic in their arguments. Okay? So the first thing that you do is, when you have a periodic function, what's the first thing that you do? Of course, you recognize that it's a periodic function, and then what's the first thing that you do mathematically? Fourier, right? You do a Fourier transform. So let's do a Fourier expansion of this guy. To the I n theta e to the I phi fine. So what I do is that I do this Fourier transform and I plug it back there. So I hope you don't mind if I erase this here and rewrite this equation here. Did you mind? No, no? Okay, you didn't mind. So what I did was, till now the only time I made an approximation is when looking at the equation of motion for this center of mass coordinates, the difference and the sum. And what I said is that epsilon is a small quantity, so this one has this solution to leading order and that one has that solution to leading order, but that was the only thing that I did. And then I did a Fourier transform, which is definitely not an approximation. And there is an epsilon here. Now I claim that if I want to know the leading contribution of this term to the dynamics of theta k, then what, or let me not claim, let me ask you. If I want to know, since epsilon is a small number, and I want to know to leading order, how does this term contribute to the dynamics of theta k? So then I am asking what I should substitute for theta and phi. Can I somehow make this equations to substitute for theta and phi here? I mean, what is the thing that I should substitute for? There is already an epsilon sitting here to leading order in epsilon. I just substitute the 0th order solution there, right? Because there is already an epsilon there. There will be an epsilon plus epsilon times something plus epsilon times something. But if I substitute those epsilon correction terms here, I will get a correction of order epsilon square. So that is not the leading one. So the leading one is what I do is that I take those things and I put them here. That will give me the leading contribution to this term. So therefore this one will now look like omega k plus epsilon approximately to leading order in epsilon. So let me say approximately means to the I n of m fine. Now let's focus on this term. And ask for its, how does it change as a function of time. So from this term I can clearly identify two time scales in the dynamics. Can you tell me what are those time scales? Absolutely. So there are two time scales in the system. So there is one time scale, let me call it tau 1, that is equal to 1 divided by omega 1 plus omega 2. There is another time scale tau 2, which is 1 by omega 1 minus omega 2. I take the mode of it, okay? Because it doesn't matter, because anyways m goes from minus infinity to plus infinity. If it is negative, I just switch sign. Can you tell me of these two time scales, which is the smaller of the two? Tau 1, right? So tau 1 is much smaller than tau 2. Surely, I mean, whatever be the, see, the sign is not so much a problem of the frequencies, because I can always redefine my theta. You know, negative frequency just means that it's going in the other direction. That's not an issue. So tau 1 is much smaller than tau 2, because here I'm talking about difference, but here I'm talking about the sum, and therefore this term is definitely much smaller than tau 2. So therefore, if I am interested in a time t, let's say, which is in this window. How many of you have read or at least referred to or seen, maybe, okay, it's milder even, Feynman's lectures on statistical mechanics? Okay, so one full and one half, so you have heard about it probably. Okay, so Feynman gives a very, there's a clean definition of equilibrium that he mentions at the beginning of the first chapter, that when all the fast processes have already happened and the slow ones are yet to happen, and it's a long sentence, but I just take the first part of it. Say that, you see, what is it that you are interested in? You are interested in the dynamics of the system over times in which all the fast things have happened, because the fast things are very fast. For example, when I want to know what is going to happen to my life, I don't care much about what the atoms and molecules are doing, because they would do whatever they would do, but by the time I blink my eye, they would move around and go somewhere for a ride. But I would like to know, the fast processes are fast, so I can just forget about them. They have already happened. By the time I, stop talking about them, they are already. But the slow ones are yet to happen, and these are the slow ones. The slow ones are the ones that are going to dictate the dynamics of the system, because the slow ones are yet to happen. They haven't yet happened. Maybe there's going to be some, no, let me not predict something. Okay, storm, let's say, which is, and then I'll probably have to, do something, etc. So therefore, I should be interested in times which are longer than the time scale for fast processes, but then shorter than because if I go here, when everything happens, then it would be a dull thing. So whatever has to happen has happened. So I am somewhere here when the fast ones have already happened and the slow ones are yet to happen. So let's see what the fast, so this is the fast time scale, right? And this is the slow one. So what does this fast time scale do? Well, what would this term do? This is the term that changes over a fast time scale. What it does is that, of course, e to the I theta, it doesn't have much of a freedom. It just goes between -1 and +1. Okay? And then it just oscillates, because it is e to the I. So if I write it out, it's cos plus I sine. So it just oscillates between -1 and +1. And what I said is that this is a very short time scale. So what will happen is that this term, the fast term, it would oscillate, over this time, it would oscillate many times over the time scale of observation. While the slow one is, it's very slow, so maybe it changes only a little bit and so on. Doesn't do much. So what I can do is that, since the fast ones will change a lot of times, and it's a function that is oscillating between -1 and +1, so if I take the average effect over time t, I will get basically 0. Because in time t, the function, this term, this first term, will change its sign many times. So therefore, I will get basically 0 unless something is not true. What is not true? This term will change its sign many times unless something is not true. Absolutely, unless n is equal to 0. If n is equal to 0, then there is no oscillation. Okay? But the remaining ones I can just forget. I can just integrate out, because they will change, they will give me some 0 contribution. Okay? So what I do is that I therefore choose my time scale of observation to be this one, and I take this one and I average it over a time window which is here, between this and that. So what I do is that I take this equation and I take its time average, which is defined to be this guy, 1 over t, my time scale of observation, 0 to t of dt of d theta k dt. Okay, so what I do is that I take this equation and I do that integral. Of course, the first term will just give me omega k. And what will the second term give me? If I just write it out, I'll get epsilon by t summation n if I cheat, then do catch me, if you can. No, you will. I mean, it's not so difficult to catch. This is of course exact, but then what I said is that, okay, over this time scale, this number will change its sign a lot of times. So therefore, what I can do is that the only term that will not change its sign is the one that corresponds to n equal to 0. Okay, so if I do that, then this second term, it would let me go up. So the second term will be what? Epsilon by t of 0 to t. This argument is clear, right? That I need to take out the contribution corresponding to only n equal to 0. Because when n is not equal to 0, it changes its sign so many times that you will get, you'll get just 0. Okay. And this is, by the way, it's a slow term. It will not change much. Only this term will do all the mess. So it is, what did I write? Okay, yeah. Sorry. So this will be epsilon by t summation of g tilde k n equal to 0. So I put n equal to 0 here. M remains whatever it was, minus infinity to plus infinity. This times dt times e to the power I m omega 1 minus omega 2 t by 2. This is just the second term. But this integral can also be significantly simplified. What do I need to do this integral? You remember that t is in that regime. Does the integrand change a lot over this window? No, because this time scale, this time is much smaller than this time scale. So I can just pull that out. It doesn't change much. So if I do that, then I get just epsilon times summation over 0 m, sorry, m equal to minus infinity to plus infinity of g tilde k 0 m, and if I pull that out, that t cancels with this integral, so I get e to the power I m omega 1 minus omega 2 t by 2. Huh? No, m I am keeping, no? M I am not doing anything.
Yeah, but the frequency, I mean, you have different terms, and for some of them, for high M, it may change quite a bit.
You see, since I think I am in good shape because I take my time to be in this regime. But you see, tau 2 is 1 divided by, okay, maybe not all terms will contribute. Some terms you can forget about, okay? But anyways, I mean, it's not such a bad approximation. What you are saying is that if m is very large, then even if, t is much smaller than this one, I mean, those terms will not contribute. Okay, I throw them away. Doesn't matter really. So therefore, I end up with an equation which is of the following sort: d theta k dt average is equal to, and I am almost done, not with the lecture but at least with the derivation. This would be omega k plus epsilon times summation g tilde k 0 m, m going from minus infinity to plus infinity, of e to the I m t. And what is the term that I have here? I have omega 1 minus omega 2 t by 2. So let me not write t here. And there is an epsilon sitting here. So what I can do is that I can replace that omega 1 minus omega 2 t by 2 with what? You remember we had talked about these two variables, theta and phi, capital theta and capital phi. To leading order in epsilon, the solution for the difference was omega 1 minus omega 2 t by 2. Okay? So therefore this one will be what? So if I just replace it, this one will be phi t. Okay? And this term, see, I can forget about the angular brackets, because I don't want to keep writing the angular brackets. I know that what I am talking about is the long time dynamics of the system. So therefore, I can simplify the notation and just write the equation of motion as d theta k dt is equal to omega k plus epsilon times a new function, let me call it q of k. If you remember, phi was the difference, so this one will be theta 1 minus theta 2. And there are two such equations. So you see that what I was able to show fully in this lecture is that when you have limit cycle oscillators and there is weak interaction among them, then the interaction has to be of this following form. It has to be expressible in terms of the difference in the phases of the different oscillators. Okay, this is for 2, you can generalize it to more than 2. Okay, that derivation is slightly complicated. In fact, the derivation that I presented here is also a back of the envelope calculation. If you want to go through it in full rigor, you have to read the book by Kuramoto. I think Kuramoto wrote a book only on the derivation of this model. Okay, so because these are not Hamiltonian systems, you don't have any guiding principle. So you have to do, so this is what is known as phase approximation method. Okay, and basically what we did was we invoked the time scale separation. We said that there is a weak, there's one time scale that corresponds to the inverse of the difference in the frequencies, and the other one 1 divided by omega 1 plus omega 2 and so on. Okay, and if you, so this one was for 2 oscillators, and if you do it for many oscillators, so this equation will generalize to the following form. Let's say for every pair, see here, this was the function for, I just had one pair. For one pair, it was the difference of the phases between the, difference in the phases of the 2 oscillators. So if you have many oscillators, so this you can define a function qij, which will be a function of theta I minus theta j. Okay, and then you sum over all j from 1 to n. Suppose there are capital N number of oscillators. N can be 2, 3, 4, etc. And of course, you would like to exclude the case j is equal to I, because, oh sorry. There has to be a small parameter somewhere, because otherwise this approximation does. So Kuramoto took the following attitude that, okay, this is like again very general, okay, but then what do you do? Okay, first of all, you have a coupling function that couples the ith and the jth oscillator that depends on the pairs that you have chosen. Okay, because this is If you take this and if you generalize it, you do it, you get this way. So what you do is that you say that maybe the function is the same. So okay, so what is the idea? The idea is that, of course, I mean, if you put in all aspects of complexity and ask, do I get synchronization? Yes, there is a good chance that you will get synchronization. But the question is, what are the minimum ingredients that you would like to have? What are those ingredients that you would like to have in the model which are minimal, yet they are able to predict synchronization? Then that would be a surprising thing, no? That you threw away so many ingredients and yet you are able to capture the essential dynamics. Okay? So the first thing what Kuramoto said is that let me not take this function to be different for different pair. Let me just take it to be the same for every pair. Okay? So the equation will be d theta I dt equal to omega I plus epsilon times summation j equal to 1 to n q of theta I minus theta j. I threw away the ij here. I can keep it, but then that's complicated. So let's just do this. Now, what is the best way to invoke weak coupling between them? The best way to do is to say that, well, for every pair, the coupling is inversely proportional to, namely, you do this one. That's the best thing that you can do. That between the pair with frequency omega 1 and omega 2, what is the coupling? The coupling is k over n. So as I make the number of oscillators, as I start dealing with a larger and larger number of oscillators, the coupling between a pair of oscillators is scaling down with n. But that's fine, because if I ask what is the cumulative effect of all the oscillators on one oscillator, that would still be of order 1. Why? Because there is an n here and this is a periodic function, so this would be either a sine or a cosine. So this term, the summation would itself be of order n. So therefore, n divided by n is of order 1. So that is to say that between every pair, if I ask how are they interacting with one another, it's very weak. But if I ask how do I interact with I don't know, a coffee shop owner in Barcola, I don't even know. But there is a cumulative effect of the city of Trieste on me. Okay, so this is the way you do it. And what is the function that you choose? See, you cannot do analytics with this one, because okay, maybe you fixed it, you said that there is no, the function is the same and weak coupling, etc. But then what do you do next? I mean, you have to do some, you should be able to do some calculation to show that you are able to get synchronization. So the first thing, or the simplest thing that you can do is you have to have this function to be a periodic function. So what Kuramoto did was he chose it to be a sine function. So q of theta, and I'll tell you in a minute why it has to be a sine function. So you choose it to be I minus theta j. Just 1 minute. Yeah, sure, you can ask. 1 minute. Just give me 1 minute. So then if you just plug this here, the equation of motion becomes d theta I dt equal to omega I plus, you may ask why, probably you want to ask something else, but let me, just give me 1 minute. Why did Kuramoto choose it to be a sine function? Why not cosine? Because you see, what I want is, I know that when there is no coupling in the system, there is no way in which I can have synchrony, right? Because this we saw, that then the phases will just change and there is no hope that the phase difference between the different oscillators will be a constant independent of time. So somehow interaction has to do the magic, okay? And in fact, if I choose it to be a sine function, it exactly does that magic, because sine has this property that if theta j is equal to theta I, then this term is 0. So you seem to have a way to, and we will analyze it in more detail tomorrow, you have a way to bring the oscillators closer in terms of their phases. This one, if you make it cosine, it has just the opposite effect. It would try to push them apart. Sine would try to pull them together. Cosine would, why not 2? sine 2 theta. Why not, do an expansion and keep all sine theta, sine 2 theta, sine 5 theta, 76 theta, everything. You can do it. But then it would be better if instead of putting all those complications, I am able to show in this very simplistic setting that there is indeed synchrony in the system, then it would be even more amazing, no? That you did not put in all the factors and yet you are able to do. And tomorrow what I will do is I will show how does one solve this dynamics. Definitely you cannot integrate these equations of motion, highly nonlinear equations because of this sine function. You cannot say that theta j is equal to theta I and therefore I keep sine to first order. That's a very crude approximation. How do I solve this equation? So of course that was one problem that kept Kuramoto and Strogatz and many people Crawford, many people occupied for several years to come up with a theory that is able to show that if there is an order parameter that I am able to define, which is roughly speaking the fraction of the total number of oscillators which are synchronized. Synchrony in the same sense that fraction of the phases, total number of phases which are going around, keeping a constant phase difference among them. And what Kuramoto showed is that if you plot it as a function of k, definitely when k is 0, there is no hope that the system can be synchronized. And what he was able to show that this system shows a bifurcation at a critical value of Kc, namely that there is a range of coupling constant k, this is called the coupling, namely 0 to Kc where the system does not synchronize, but then there is a critical value of Kc which he was able to compute. It is given by this, we will derive tomorrow, so do not get scared if I, just to impress you, I wrote down the formula to show that there is a synchronized solution that bifurcates continuously from this unsynchronized solution, and of course the fraction can take at most the maximum value 1, so this is the value 1. Okay. This of course is true when you make the, when you take the take the number of oscillators to be very, very high. If you take 3 or 4 oscillators, then it would be something like this. You won't get a clear signature of a bifurcation. This is not a phase transition, so I just emphasize that you cannot interpret it as a Hamiltonian system in some potential and then you minimize the free energy or maximize the entropy. There is no noise here. This is not even a Langevin equation, and so you cannot write down a Fokker-Planck equation, set the left hand side to 0 and do all those tricks and say that, oh, but I have to maximize the entropy and minimize the free energy, and whatever I get by doing so is the equilibrium stationary state. No such thing is going to be applicable here. Either you integrate these equations exactly, which is impossible, or you come up with an alternative theory, and the theory should be good enough to address not just this problem but also the case where when you have not just sine theta but sine 2 theta. So I hope, by the way, this is known as the Kuramoto model, and as I mentioned in my first lecture, Kuramoto was awarded the Boltzmann medal this year, which is the highest award in statistical physics. But of course, this model is derived in a monograph that he wrote. It's called Chemical Oscillations, Waves and Turbulence. The whole monograph is devoted to just deriving this equation. Okay? Yeah, somebody had a question. Yeah.
The reason why we have transferred from Qij to Q is that we are trying the easiest possible model to see if it's able to.
Yes, yes, yes. See, you can play with it. You can say that, look, this one means that every guy is interacting equally well with everyone else, but then you can put them on a network and say that Qij, okay, what I do is that I put in some distance metric. If the oscillators are close enough, then there's strong interaction. If they are far apart, then the interaction is small, and so on and so forth. But these are added complications. And as you may add more and more ingredients, the analysis is going to be more and more difficult. Okay, are there other questions? I strongly urge you to read a very nice review that Strogatz wrote on this subject. It's called, I mean, it's there in the list of references that I provided in my first lecture. It's a 20-page article. It's called From Kuramoto to Crawford and something, but it gives a very nice idea and an overview of the field of synchronization. And there is also a very popular book on this I should have mentioned, maybe it is there. It's called Sync by Strogatz. Sync and then something. There is also a subtitle which I don't remember. It's a popular level textbook. He talks about synchronization in various aspects of life and what can be done and cannot be done and so on. Okay? So thank you for your attention. Yes?
Okay, I remind you that this afternoon this room will be used by another activity, so don't leave anything here. And then if you need a room, you can use the computer lab, okay? Or say other rooms. And and don't forget to put your preference for the lunch, dinner.
Maybe this one, no?
This one.